Okay, continuation of this lecture on the Mobius inversion formula. So here's the formula for Mobius inversion. As I stated, it's called an inversion formula because it sort of inverts the big F and little f as far as what's being solved for. And it does this by introducing a specific function or making use of a specific function, which is in particular the Mobius mu function. So let's go ahead and discuss the proof of this particular seemingly really complex type of a formula. Okay. So let's go ahead and get started here. So here's the hypothesis. I'm going to write it out because it includes information that we definitely will need in our proof, and that is that if we let big F and little f be number theoretic functions related by big F of, let's say, n is the sum across all divisors of little f of n, or f of d here. So this is the preamble, the givens. Then okay, so the result we're after here is the Mobius inversion result, which is that f of n is equal to the summation across all divisors of the Mobius function evaluated, and the sum up here evaluated at n over d. This is actually equivalent to this statement, and I hope that you can see why these two are equivalent. What we're basically doing is flip-flopping where d and n over d reside, and to give a quick sort of idea here is that if say n is equal to 10, then d and n over d, of course these are just factor pairs, right? 1 and 10, 2 and 5, 5 and 2, and 10 and 1. So d can be any of these numbers, n over d can be any of these numbers once d is chosen. So it really doesn't matter. What we're doing here is literally summing mu of 1 times big F of 10, mu of 2, big F of 5, mu of 5, big F of 2, mu of 10, big F of 1. And so which one we designate as d and which one we designate as n over d really doesn't matter here. And you'll see that come up in the proof, actually. So here is our proof. So in the proof, we simply have to look at what I'm going to do is I'm going to start with the right-hand side and solve for the left-hand side. So we look at the value of, and off to the races we go here. I'm going to pick the right-hand side here, the sum across the divisors, the Mobius function times the sum of some number theoretic function n over d. Well, so let's just think about this. Well, we know what this guy is. This guy is just that, right? So we can think of it this way. We can think of it as this is the sum across all divisors of n of the Mobius function evaluated at those divisors times the sum. Now, be careful, this is the divisors of n here, but here, we're evaluating for n over d, so it would be all of those c's that divide n over d. Let's introduce this variable c, f of c. So I'm simply using the definition of big F in this location in the formula, which if you think about it, we can move this mu of d inside here, right? I mean, there's no reason why we can't put the mu inside and put the two summations out in front. So d divided by n, and then c for all of those n over d's. And what would we have here? Mu of d times f of c. So I've just pulled the summation out in front. And here I'm going to argue that, we really, we don't need to have, since n over d and d itself are interchangeable, the sets of d's and the sets of n over d are the same. I'm going to go ahead and swap these and just call this c, and let's see, d into n over c. So then it would be, instead of mu of d, since d was here, I'll put a mu of c there. And then I'll go ahead and put an f of d here. Oh, no, actually I want to keep those the same. So that's right. Because these sets are exactly the same, I don't actually have to swap these two. It doesn't really matter which of the two. So I'm going to keep it mu of d and f of c. Sorry about that. The summation is the only thing that changes, right? And since we think of these things as going hand in hand with pairs, it's okay to switch the index, I guess, of summation here. And okay, so I'm back on track here. So I'm going to go ahead and bring the f of c out in front. We have c divided by n of f of c. I'll let the summation of d into n over c of mu of d. And here is kind of an interesting aside. So this guy, if I come over here and just say, well, we already know what happens here when you sum all of the Mobius mu function across the divisors of a certain number. We know that the only time this returns anything other than 0 is when when you sum across the divisors of when the number in question, I guess, is 1, right? So that means if the number in question is 1, then n over c has the only time I'm going to get anything out of this is when n over c is 1, right? So I'll just say here the only time this I guess term is non-zero is when n over c is equal to 1, right? Or when n is equal to c, right? So literally the only time we get anything that's non-zero here is when n is actually equal to c. And when n is equal to c, of course, then n over c is equal to 1. And I'll just say when n over c is equal to 1, the term is, I guess the summation here, the term is equal to 1 as well, right? So this guy is equal to 1 when n over c is equal to 1, and when n over c is equal to 1, n is equal to c. So what do we really get? Well, we get the summation for when c is equal to n of just f of c, right, times this guy, which is equal to 1. And of course, when c is equal to n, there's only one term to sum, and that's f of n. And so we've just proven what we've been asked to show, and that is that if we want to solve for f of n, we can do so by summing across this product, which is exactly what the result of above is stating. All right, that's the proof of the Mobius inversion formula. I'll stop there, and we'll do another video to finish out the chapter.